So we're going to look at circular motion, both some theory and also some applications. We'll go through this handout, which was an assignment that was given to you, um, and you can hopefully pause and complete questions as needed, or just review your answers that you've already done. So question one says, it is possible to spin a bucket of water in a vertical circle and have none of the water spill when the bucket is upside down. How would you explain this to members of your family? So the scenario is you have a bucket with water in it, moving in a circle. The concept here is that at the top of the circle, the centripetal acceleration is at least 9.81 meters per second squared. It could be greater, which means that at the top of the circle, the rope or the chain or whatever you're swinging the bucket with is applying a downwards acceleration of 9.81 meters per second, which is at least that of gravity, which means that the water in the bucket is not falling faster than the bucket itself, which means that the water will never fall out of the bucket. If you go 9.7, you'll start to get some water falling a little bit faster. But this is demonstrated very well by taking a plastic cup, puncturing the bottom of that cup, and filling it with water. Um, if you hold the cup steady, the water will continue out in a steady stream. But if you drop that cup with the stream, you'll notice that the droplets of the stream do not continue in a steady stream. They break into droplets because the water doesn't exit the hole because the cup is falling at G as well. So the bucket is being at an acceleration but greater than 9.81 meters per second, um, which is gravity. So it says water spins off a rapidly turning bicycle wheel. Why? Um, you've probably seen this effect when you were out on a bicycle before after a rainstorm or in the rain, and you'll notice that you always get the watermark or the mud watermark up your back. The reason is very simple. If you have if you have a wheel, and there's droplets of water on it, which are exaggerated in this photo, the adhesive properties of water attract the water to surfaces. So water wants to stick to things. If if the centripetal force is greater than the force of adhesion, whatever that might be, then the water droplets can't stay stuck to the wheel anymore and they will continue moving in a tangent line. Which is why you get the water streak up your back. In a dramatic circus act, a motorcyclist drives his bike around the inside of a vertical circle. How is this possible considering the motorcycle is upside down at the top of the circle? So again, it's probably something you've seen before where you end up with a motorcycle upside down in a loop-de-loop. The concept is exactly the same as the water in a bucket. That FC if FC is greater than FG, then that means that the track is pushing down harder than gravity, so the actual track will move down with the biker, keeping contact the entire time. As long as the biker is achieving that same acceleration. In other words, acceleration due to centripetal acceleration needs to be greater than or equal to G, and the explanation is exactly the same as part one for that. The gravitational pull of Earth is only slightly less at an altitude of an orbiting spacecraft than it is on the Earth's surface. Why is it then that astronauts feel weightless? And the answer is simply they are in they're in free fall. So they basically fall towards Earth. So here's Earth, here's our little spaceship, and the when something is orbiting, it is obviously doing a circle around a planet or a star or moon, but it is moving at a direction tangent to its circular motion, its velocity at any given instant. But the curvature of the Earth pull basically means that the land falls away from the spacecraft at the same rate that the spacecraft is turning towards it. In other words, as the spaceship falls towards Earth, the Earth curves away from it at the same rate, which means that a spaceship or the moon is constantly falling towards us, but it will never hit us because we are curving. So the minimum speed for that is described by circular motion. So the answer is to why they feel weightless is they're in free fall at all times, but they'll never hit the Earth. In the movie 2001: A Space Odyssey, a rotating space station um, provides artificial gravity for inhabitants. How does this work? Very similar to the question on the motorcycle. The outer walls push inward, applying a normal force. This normal force is approximately equal to the weight they would feel. So they don't actually know. So the outside walls of the spaceship are pushing inwards. So their little feet are on the outer walls, standing on the outward walls. The spaceship is rotating, and the rate that the FC is pushing inwards is equal to the normal force that they experience on Earth. Therefore, they think that there is gravity. So in question 6, it says, in Robin Hood's Prince of Thieves, starring Kevin Costner, Robin swings between trees on a vine that is on fire. At the lowest point of his swing, the vine burns and shows Robin begins to fall. The next shot, from high above the trees, Robin is falling straight downward. Would you rate the physics in the scene as good, bad, or ugly? So we have somebody, in this case Robin Hood, swinging. And when he gets to here, the rope breaks, and then his velocity is carrying him downwards. So the physics in this particular scene is extremely ugly, because we know from what we've been doing in class is that at the bottom of that loop, his velocity should have carried him um, tangent to his motion. Not perpendicular to it. When rounding a corner on a bicycle or motorcycle, the driver leans inward towards the center of the circle. Why? So you have a, a bike kind of leaning inwards. And what is happening now is the normal force is going to be pushing equal and opposite backwards from how they're applying their force. There is a horizontal component of that normal force that is pushing towards the inside of the circle. That horizontal part of the normal force that is now being applied inward is that much less horizontal force that the friction needs to apply on the wheels. So to make the turn, they're going to have the horizontal component of the normal force plus some force of friction due to the tires, and together they're going to give you centripetal force. If they tried to make the turn without leaning over, this particular component of the vector wouldn't be there. So they would have to go slower, or they would spin out. So they lean in. So the horizontal part of the normal force helps make the turn. So for number 8, it says a car drives with a constant speed in an elliptical track, as shown below. Rank the points A, B, and C according to increasing likelihood that the car might skid. Indicate a tie if appropriate and explain your choices. So remember what you're seeing here is here's the center of a circle, and you can kind of expand the circle to show what the radius is. The radius at C, the radius of B, and the radius of A are actually different because of the fact that this is an ellipse. So the radius of C is greater than the radius of B, which is greater than the radius of A. That means that centripetal force at those points would mirror that. So the centripetal force at C is greater than the centripetal, is less than the centripetal force at B is less than the centripetal force of A. So the maximum centripetal force in this scenario is going to take place at point A, meaning that you need the most effort to make the turn. So you are most likely to slip at A and least likely to slip at C. So the order is C, B, and A. When you look at an ellipse, realize that the radius is different at those 3 points, and that would be the key to that particular question. A car is being driven with a constant speed around a circular track. Is the velocity constant? No. The direction is changing. For B, is the magnitude of the acceleration constant? Yes. V squared over R would not change. And for C, is the direction of the acceleration constant? This is sort of one of those questions where you could answer it in 2 ways, yes or no. Yes, it's constant because it's always going to the center of the circle, but most people will write no, it changes to point toward the center. And that would be all of it for question 9. So what we're going to look at now is just another question where we're using theory to figure out the order of or likelihood of something happening. It says humans lose consciousness if exposed to prolonged accelerations of more than 7 Gs. This is a concern of jet fighter pilots, where they're going to experience centripetal accelerations of this magnitude making high-speed turns. Suppose we would like to decrease centripetal acceleration of a jet. Rank the following changes in order of how effective they are in decreasing centripetal acceleration. We'll start with the least effective. So, to decrease the turning radius by a factor of 2. So remember what we're doing here. AC is equal to V squared over R. So for A, AC is equal to V squared over 1/2 R is AC is equal to basically 2 times. So for A, that would actually double the centripetal force and centripetal acceleration. For B, to decrease the speed by a factor of 3, so AC is equal to 1/3 V all squared over R is equal to 1 over 9 V squared over R is equal to 1 over 9 V squared over R. So for part B, the centripetal acceleration would be 1/9 of the original amount. Finally, for C, if we decrease the speed by a factor of, increase the turning radius by a factor of 4, AC is equal to V squared over 4R is equal to 1/4 V squared over R. So that would quarter it. So to place it in order, A would be the least effective, then C, then B. just put them in order based on which is going to be the biggest AC to the least, the smallest AC. For question 11, when you take your 1200 kilogram car out for a spin, you go around a corner with radius 57 meters. Assuming a speed of 15 meters per second and the coefficient of static friction between the car and the road is 0.88, assuming your car doesn't skid, what is the force exerted by static friction? So we're going to assume that the car is just making that turn. So Fc equals mv squared over r is equal to 1200 kilograms, 15 meters per second squared over 57 meters equals 4736.84 newtons. Fc must be provided by the force of friction on the tires, and that's equal to 4.7 times 10 to the 3 newtons. We didn't even need that. Question number 12. Find the speed at the bottom of a test tube in a centrifuge if the centripetal acceleration is 52,000 times acceleration due to gravity. The distance of axis of rotation to the bottom of the test tube is 7.5 centimeters. So AC is equal to 52,000. G is equal to 52,000 times 9.81 meters per second squared is equal to 510120. Velocity is equal to AC times R is equal to the root of 510120 0.075 195,599 is equal to 2.0 times 10 to the 2. So it's going to be moving at about 200 meters per second to generate that force. To test the effects of a human body, NASA has constructed a large centrifuge at the Manned Spacecraft Center in Houston. In this device, astronauts are placed in a capsule that moves in a circular path with a radius of 15 meters. If the astronauts in the centrifuge experience a centripetal acceleration of 9 times acceleration due to gravity, what is the linear speed of the capsule? So V is equal to AC times R. AC is equal to 9G is equal to 88.29 meters per second squared. Use that number down here. 36 meters per second. So now we're moving on to number 14. Number 14 is where we start dealing with bank turns. The equation for a bank turn is the tangent of the angle is equal to V squared over RG. So when we do this, we can rearrange this to solve for the radius that the question is asking for. The radius is equal to V squared over G times the tangent of the angle. That's equal to 22.7 meters per second squared over 9.81 times the tangent of 31.5 degrees, 85.7 meters. Jill the Jungle swings on a vine that is 6.5 meters long. What is the tension of the vine if Jill, whose mass is 61 kilograms, is moving at 2.4 meters per second? So if you have someone hanging from a vine swinging with a speed in this case of 2.4 meters per second, at the bottom of her loop, she has two things to consider. So the rope has to support her weight, first of all, but it also needs to provide the force to keep her moving in a circle, Fc. So at the bottom of the rope, the tension is equal to Fg plus Fc, or the tension is equal to her mass times g plus v squared over r equals 61 kilograms, 9.81 plus 2.4 squared over 6.5 equals 650 newtons. If you don't take into consideration the gravity or weight at the bottom, the rope will break. So it's very important to realize that at the bottom, gravity is working against her, so she'll feel heavier. At the top, gravity is actually helping make the turn, so she'll feel lighter. And that leads us into question 16, part A. At the top of a Ferris wheel, your weight will actually be lighter than it will be at the bottom. Explain this difference. So if you have a Ferris wheel and a seat here and a seat here, we have a radius of 7.2 meters, and we are moving at some speed. So to figure out the circular speed, we just write the formula for circumference over period, and that's equal to 2 times pi times 7.2 meters all over 28 seconds. VC is equal to 1.61 meters per second. So there's the circular speed. So the Ferris wheel is rotating in a circle at 1.61 meters per second. At the top of this circle, the gravity or the weight of the rider is pushing down with a certain amount of force. Now, if I were to take a seat and just put it up off the ground, 14.4 meters up off the ground, and the seat would go down, it would go towards the center of the circle. So gravity is actually helping you here. At the bottom, it's just like the problem with Jill of the Jungle, where you have to provide the normal force plus a little Fc. So you have an additional force required to make you go up, but gravity helps you on the way down. So on the way down or at the top, you will experience a force of the mass times g minus v squared over r. And at the bottom, you'll experience a normal force of m times g plus v squared over r. So top and bottom. So the top is 55 kilograms, 9.81 minus 1.61 squared over 7.2 meters. So at the top of the Ferris wheel, the normal force experienced will be 520 newtons. At the bottom, 9.81 plus 1.61 squared over, it'll equal 560 newtons. So they would feel heavier by 40 newtons at the bottom compared to the top. So as far as A and B, and this is really part B here, as far as the explanation goes, and I'm just not going to write it out, but at the top, gravity is pointing towards the center of the circle, which means that much less force needs to be applied to make you go in a circle, to just take gravity away from Fc. At the bottom, it's Fc plus the normal force to cause you to go up, so you have to add them together, and that's what we've done. So driving your car with a constant speed of 12 meters per second, you can picture this as a giant circle. When you hit a bump, and you can experience that around various roads in the county, you're basically moving in a circle. So in that particular case, it's just like the top of the Ferris wheel. The gravity is helping you move down from the top of the bump, so the road doesn't have to push up as hard, therefore you feel lighter. So the normal force in this case, 67 kilograms, 9.81, take away 12 squared over 35 meters. The normal force that we'll feel is 382 newtons, which is just slightly less than the actual mass of the person. So the exact opposite of this would be true. If it was a dip in the road, you would use the similar equation as the bottom, where you would add them up because the road has to push up harder to bring you back up. So question 18 is very similar to what we've already done with demonstrations in class. You want to swing a 4.5 kilogram bucket of water in a vertical circle with a radius of 1.1 meters. What speed must the bucket have if it is to complete the circle without spilling any water? So A, as soon as we're asked a question about a vertical circle and we have to keep something in the bucket, we know that AC is going to be equal to G, which is equal to V squared over R, which is equal to 9.81. So we'll use this expression. So V is equal to AC times R, take the root of it, and we've used this several times already, is equal to the root of 9.81 meters per second squared times the radius, 1.1 meters, and that gives us 3.3 meters per second. So part B asks me, how does the answer depend on the mass of the bucket? And the answer is very simple. It doesn't. It doesn't matter how much mass is in the bucket. It just matters the speed it is moving. Now, the tension of the line, that would matter, but the speed doesn't. The energy that you're going to expel spinning a heavier bucket over a lighter one is different, but the actual 3.3 meters per second is irrelevant. So for question 19, we have a really cool little demonstration. You take a little hook, and you put a little rope, and you attach a little plane, and it moves in a circle. It moves in a circle, and that the rope forms an angle. So we can do this very, very simply using the tangent theta equals v squared over rg1. But let's have a look at exactly why that works and where it comes from. So for part A, we know the plane is moving, so it's not exactly a statics problem. So first of all, we know that the plane has weight, and that's equal to mg. We know that this line has some sort of tension on it, and this force here, the j hat force, is going to be equal to the cosine of the angle times tension. The opposite side, which is the vector pushing inward, which is the centripetal force, is going to be equal to the sine of the angle times tension, and that's my horizontal component. So the sum of the forces in the I hat direction, so what do we have up here, is equal to the tension sine theta. But we know that this is the vector pushing towards the center of the circle. So this is circular motion. So this is also going to be equal to mv squared over r. So in the horizontal direction, we know that the t sine theta is equal to centripetal force, mv squared over r, which is what this is. So now we look in the vertical direction. So the vertical direction, I know that I'm going to have mg negative going down plus t cos theta, and that has to equal 0 because we don't want the plane moving up or down. So I'm just going to rearrange this equation and solve for t. So t is equal to mg over cos theta. So that's me taking this equation here and just rearranging and solving it for t. Now I'm going to go up and use this expression but sub in my t value. So t sine theta is equal to mv squared over r. mg over cos theta, sub my t in for it, times sine theta is equal to mv squared over r. So the mass cancels out on both sides, and I end up with g sine theta over cos theta is equal to v squared over r. I'm going to divide both sides by g, and I end up with sine theta over cos theta is equal to v squared over rg. Sine theta over cos theta is the tangent of the angle, is equal to v squared over rg. And there we go, we have that equation. So it's a lot of work for something that we already knew. But now we can go ahead and actually use it. Let's use the space up here. Theta is equal to the angle whose tangent is 1.21 meters per second squared over 0.44 meters times 9.81 meters per second squared. Theta is equal to 19 degrees. So when you get a question like this that you know you're at an angle, you can jump and use this equation. This is just sort of elaborating on where it comes from. So then for question B, which it helps that we've already done the work up here for question B, it says, what is the tension on the string? So I'm going to use this expression that we already created. Tension is equal to mg over cos theta is equal to 0.075 kilograms times 9.81 meters per second squared over cos of 19 degrees equals 0.78 newtons. And there's a nice and simple explanation for what we have come up with. So this is a ride that we used to see in Moncton in Crystal Palace, where you have a swing operating in a circle. And the neat thing about this particular ride is that the mass of the rider didn't really matter. The angle was always the same regardless of the mass of the rider. So we're going to have a quick look at that as to maybe we'll try and figure out why that is. So it says a popular ride at amusement parks is shown below. In this ride, the people sit in a swing that is suspended from a long rotating arm. Riders are at a distance of 12 meters from the axis of rotation, and you can see that is shown here. We move with a speed of 25 miles per hour. Find the centripetal acceleration. First of all, 25 miles per hour times 1.6 kilometers per mile gives me kilometers per hour, and then we just divide that by 3.6 and I get 11.1 meters per second. So just 25 miles per hour is 11.1 meters per second. So find the centripetal acceleration. AC is equal to v squared over r is equal to 11.1 meters per second squared over 12 meters is 10 meters per second squared. B, find the angle supporting wires would make. So this time we're not going to go through the whole derivation of this equation. We're just going to use it. Tan theta is equal to v squared over g. We'll substitute in our values at 11.1 meters per second squared times 12 meters times 9.81 meters per second. 1.046. So the tangent of this angle is 1.046. Theta is equal to the angle whose tangent is 1.046 That's equal to 46 degrees. So one of the things we should notice is that at no point here did we use the mass of the rider in this equation. And that basically is the answer for letter C. It says notice that the swing is at the same angle regardless of the rider. Explain. So if you look at number 19, you'll see that the mass actually cancels out. And at no point during this calculation does the mass factor into our problem. So we move on to question 21. It says, as part of a circus act, a person drives a motorcycle with a constant speed around the inside of a vertical track of radius r, indicated in the diagram. If the combined mass of the motorcycle and the rider is m, find the normal force exerted on the motorcycle by the track at positions A, B, and C. So A is the bottom. We've done this already. Normal is equal to mass g plus v squared over r, because the track has to respond with its normal force plus the centripetal force above. At point B, the weight is here. FC is perpendicular to that. So at that point, the track just has to provide centripetal force only. And at part C, at the top, we need a certain value for FC. However, gravity is providing a lot of that, so we can actually subtract that away, and we're only responsible for this much track pushing back. So in this case, we have normal force is equal to mass g minus v squared over r. And there's no variables actually given to us, so we just go with the expressions themselves.